There's another example in your book of using the divide and conquer paradigm in order to solve some problem, specifically matrix multiplication. And I want to briefly go over this because we're going to see matrix multiplication pop up again in the next chapter. Our task here is to multiply two matrices together, matrix A with matrix B, where matrix A has dimensions D and E. So this means it has D rows and E columns, and matrix B has dimensions E by F. Now, in order to actually multiply these together, for us to be able to, then the number of columns in E must match the number of rows in B. And then as a result, after we multiply these together, we get some matrix, let's call it C, which has D rows and F columns. This is based on the outer dimensions of A and B. Now our runtime, if we wanted to compute this just kind of straightforwardly using the definition of how would we multiply matrices together, is the product of the rows and columns of A and B. Now, why that's the case, maybe if it's been too long since the last time you did linear algebra, just a quick refresher here. If we have, here's our matrix A, a D by E matrix, meaning it has D rows and E columns, and B, which is an E by F matrix, and our resulting matrix C, which is a D by F matrix. Now, how we end up computing this matrix is we'll figure out what value belongs in each one of these cells. So if we want to compute, for example, at row I, so this is at position I here, and column J, what value should be stored here, we're going to go through all of the elements in A in row I and all of the elements of B in column J and multiply them together. So let's say we have here A1, A2, and so forth all the way up until AE, since we've got E columns. And here we've got B1, B2, all the way up until BE. Well, our result will be A1 times B1 plus A2 times B2 plus all the way up until AE times BE. So we have E multiplications that we have to take and E minus 1 additions that we have to make. Now we've got a total of D times F cells in C, and for each cell we have to compute, we've got E additions and roughly E additions and multiplications. So this is how we get the total running time of, if we just use this definition of how we would compute this resulting matrix C, which is the product of two matrices, what the running time would be. Okay, we're going to see more on that in the next few videos, but what does this have to do with divide and conquer? There is a way that we can multiply. If we're multiplying two matrices together and they both have the same dimensions, so we've got an n by n matrix, which we're multiplying with another n by n matrix, using that same definition, we could come up with an n cubed algorithm to do this. We could also use a divide and conquer approach to do this. I'm not going to go over exactly the details of what that divide and conquer approach is, but this is in this section of your book if you want to look at it. But the idea for that divide and conquer approach is that it will break up the input, A and B, into a total of 8 subproblems. These are 8 matrices, and each one is of size n over 2, half the size of our original input. And then we have a quadratic amount of non-recursive overhead. Now, given this runtime, we can use the master theorem to figure out what its runtime is using asymptotic complexity. So we've got our non-recursive overhead is n squared. According to the master theorem, our critical function here is n to the power of log base 2 of 8, which is n cubed. And this is really the faster growing function. So the critical function here is impacting the running time the most. And because of this, our total running time, we're in that case that here's our faster growing function. Our running time is big data of n cubed. Similarly to how we did with integer multiplication, there is a neat kind of algebraic trick to where we don't have to use quite as many subproblems as what this divide and conquer approach that the book talks about first is what this uses. And this is what computer scientist Volker Strassen used in order to improve the running time of matrix multiplication. He realized that really we don't need 8 subproblems, we only need 7 of them. And again, this algorithm is in your book if you want to take a look at it. We're going to look at other examples of matrix multiplication later, but I just wanted to show you how we can use this runtime and the master theorem to see what parts of our algorithm, our divide and conquer algorithm, we could improve in order to get a faster runtime. And this is one example of that. So now again, using the master theorem, we have our non-recursive overhead is n squared. Our critical function that we're going to compare it to is n to the power of log base 2 of 7, which is no more than 2.808. So this is still the faster growing function, but we have something which is better than n cubed now. So we get a little bit of a better runtime. And in fact, this has often been an area of research over the last few decades now, beginning with Strassen in 1969, who improved the runtime from n cubed to this power n to the power of 2.808. And then a few years later, this was improved by 0.1. We got something a little bit better. And then a few years later, Coppersmith and Winograd improved this by 0.2. So every few years, we end up getting a little bit more of an improvement in this exponent, to the point where the latest improvement, so Virginia Vasilevska-Williams discovered not that long ago, just a few years ago, that we can multiply 2 n by n matrices together in total time n to this power. And then a couple years later, this was shown to be improved by Francois Legal to the following. And notice that at this point, this is improving by 0.000001. So the improvements that we're able to make over time are starting to decrease quite a bit. But this is a pretty hot area of research right now. And the idea is, given all of this, is it possible that we could even get to maybe one day, a decade from now, 20 years from now or something, maybe you can come up with a way that we can multiply 2 n by n matrices together in only quadratic time. Definitely we need quadratic time in order to even process an n by n matrix, because it's got n squared cells. But the question is, can we do it in only this amount of time? And based on this, we're making a little bit of an improvement every so many years, so maybe it's possible. But right now we don't know, and the best scientists right now don't know either. So. Okay, I don't expect you to know this history. This is just some kind of interesting, fun facts. We'll get to another type of matrix multiplication problem in the next slides. So if you have any questions, reach out on Piazza and let me know.